Hello, everyone. I'm Mike Urbans, and welcome to It's Your Water. Glad you found us. Today, we have a special guest interview with Derek French from Wateropolis. They manufacture a unique filtration product called CeraPure AC and CeraPure MAC, to name a few. But they're the two that we find extra special into our product line. Welcome, Derek. How you doing?
I'm great, Mike. Good to talk to you again. It's been a minute.
It's been a minute. Yeah, I know. If you're a fan of this podcast, I hope everyone listening is. Derek and I did a really good episode on CeraPure MAC and basically the background of this material that he manufactures. MAC is for iron, manganese, and sulfur reduction. So check out episode 29, and then you could circle back to this one. It's chock full of great information about Wateropolis, the ins and outs of their product line, more the science behind it. But now, let's just cut to the chase. I want to get Derek to talk to us about CeraPure AC, which we think is a very, very good tool in the toolbox. And it's a unique combination of a ceramic and an alloy and some GAC powder, a little bit of witchcraft thrown in there, but we'll let Derek talk about that. Derek, give us a quick rundown of the ceramic-based media you manufacture and what makes them unique, and segue into CeraPure AC.
Yes, well, Wateropolis has always been in the lightweight aggregate and ceramic business for filtration. We leverage some properties in ceramics, particularly surface area. Filters by definition are temporary particle storage devices. And in order to have good particle removal and storage between backwash events, you need a couple of things. You need surface roughness, gives you lots of attachment locations for particulate, whether it's iron or manganese or any other insoluble particulate. And then you also want lots of storage space on the outside of the particles. So we tend to make smaller material. If you have say you have a 24-inch deep filter bed and you have 0.5 millimeter product and a 0.25 millimeter product, two different filters, the smaller material has vastly more storage space because you have more total surface area per foot of depth of the filter media. So we tend to skew smaller in filter media size. The filter gets tighter because your interstitial spacing gets smaller. Mm-hmm. You still have the same number of, people think you have less void space, and that's not true. All filters, granular materials, have about 48% void space. Round ones, we get a little bit higher, but it just means that the voids are there. They're just smaller pieces. So we tend to work in smaller average grain size, and then we drop the uniformity coefficient, which is a fancy way of saying we take the oversized stuff out. And when you take the oversized stuff out, you get lower backwash rates, because your backwash rates are always governed by the largest grains of your filter media. And there's always variance in sizes. So as uniformity coefficient comes down, you're scalping out the oversized. So you end up with more smaller particles, again, more storage capacity. And then you drop your backwash rates by taking out those larger chunks. The ability to backwash a particle in filter grain, a receptor we'll call it, is governed by its weight and its size. Both those things influence that. So we make them smaller and we make them a little lighter. So that's how you get your backwash rates down.
So yeah, you get them. Yeah, well, that's important. Especially in the residential world, people get hamstrung a lot with not realizing they don't have enough water to backwash, and you've kind of addressed that problem with a smaller particle. So that's why we use a little bit of tighter filtration, like a garnet underneath, to capture your smaller particle. But you get a tighter bed, which is better filtration. But we addressed a lot of that in episode 29, which is really cool. So your substrate is a ceramic, correct?
Correct. Everything we do is in ceramics. And then as far as the AC is concerned, so the AC stands for alloy and carbon. So we put a coating on the ceramic that is basically, it's a 50-50 blend of copper-zinc alloy. The original brainchild behind this was leveraging the antimicrobial properties of the copper. Zinc does have some inherent antimicrobial properties, but it's a contact antimicrobial product with zinc. So that if you put a chunk of zinc on something, The zinc itself won't grow any bacteria, but it doesn't really help the areas adjacent to it. Copper is different. If you put a speck of copper onto a substrate that grows bacteria, there's actually a halo effect of disinfection radius around the copper. So we add enough alloy to keep the whole particle basically disinfected and stop it from growing biofilm. A lot of these medias become ineffective when they get covered in biofilm. So that was the original intent behind adding a 50/50 copper-zinc alloy. Of course, the other side effects we all know from popular brands like KDF, who's the brand of alloy. It's a good brand. It's been around a long time. That alloy does other things, of course, right? It has adsorptive properties on the surface for heavy metals, and it's reductive. So it takes out oxidizers like chlorine and other oxidants. So we add the alloy to that.
Yeah, but it's heavy as hell.
Yeah, it's heavy as hell. Right. So, and the interesting thing about alloys is it's a surface function. Let's assume you have a chunk of alloy the size of a marble. It's ridiculously heavy, and nothing's happening in the center of that alloy. Everything happens exclusively on the surface. By definition, that's what catalysts do. They are a non-sacrificial surface reactive product, and alloy is a catalyst. You don't need a whole big heavy chunk. You're really just using the surface of it. So what we decided to do was take that alloy, put it onto a lower density ceramic substrate, and actually give you the functionality of an alloy, but make it backwashable. I mean, at 10 to 12 gallons per square foot, you can backwash this material. Usually it's 10 in colder water, which is pretty modest. You get into a residential application where you got 2 or 3 gallons a minute, you can at least get an 8-inch tank backwashed, right?
Right.
So you end up having a filter with the benefits of the alloy. Now we add, a fair amount of alloy there. It does add some weight. I mean, we're probably adding 10 pounds per cubic foot of mass, but we're still lighter than sand by the time we're done. And we're small. We're still a small material. We're still in that 0.3 millimeter size. So that's how we're able to get it backwashed. Now, in addition to that, we also add some catalytic carbon. And the catalytic carbon is there to do some of the additional reduction of oxidizers. And that's sort of a clever way to still give it highly reactive surface, not make it too heavy and not make it too expensive. Alloys have gotten very expensive.
Oh, yeah.
Copper prices keep going up. And unfortunately, we no longer make alloys in North America. We are almost exclusively a U.S. sourced product. We are 99% raw materials, all our labor, all our packaging, all done in the United States. Except now all the alloy has to come from Germany because big companies bought up the production here, shut it down, and moved it overseas. So with the exception of the alloy, we buy it locally, but it's unfortunately an imported product. We really strive to do everything here domestically if we can.
Yeah.
So
there was some rumblings that they're going to probably bring it back to Reading, Pennsylvania or something like that, but you never know. It's a shame because I think it was originally Zinc Corp in Pennsylvania, Palmerton.
And there was an alloy producer in Tennessee. That's who we used. So Metal Powders. Royal Metal Powders was our original provider who got bought by somebody, and now it's gone. So we're always hopeful it'll come back. As soon as we have a clean, reputable source that's going to give us what we need, we don't buy anything from China. We don't buy anything from Russia. We have to go to places where we get high quality, where there's analytical data to support that. That's the world you and I live in that world,
yeah,
right? We have to keep things clean.
And we can't make it worse than what it was coming in. So, but it's a novel approach. So it's just the way you've manufactured it. Big question. Everybody's saying, wow, this stuff sounds great. What do you think are the best applications or typical applications? I can think of a few, but what do you think between us two?
So in commercial and industrial applications, we've always seen people running multimedia filters for particulate removal. Then they're running GAC to remove oxidizers ahead of reverse osmosis or nanofiltration, right? We know that RO and NF need the oxidation reduction ahead of it. And so we had this infrastructure, this multi-tank infrastructure with both requiring backwashing. The multimedias always took a lot of water. And then if you have an intermittent operation, GAC goes biological no matter what you do. There is no such thing as a GAC filter that doesn't have some biological function going on in it.
Yep.
Doesn't mean it's hurting anything, but people say, how long does GAC last? It's kind of an open-ended question. I think it lasts until it overgrows with biofilm. Once the functional sites stop absorbing and adsorbing, then it's no good to you anymore. And it certainly stops removing oxidizers. And then what happens if it's on intermittent use ahead of an RO, every time you turn that filter on, especially this happens in boiler rooms where it gets hot, and they sit for hours out in between flow rates, they dump biological film off into the feed end of your ROs, and now you have biofouling on your membrane. So this material was originally designed to consolidate the multimedia filter and the GAC filter. Now you have a really excellent 5-micron filter. I mean, you're going to get 99% removal at 10. So you're down in the 80s for 5-micron removal.
That's the ceramic part of it. Yeah.
Right. And now you're removing oxidants because you got alloy and you got catalytic carbon. And the alloy prevents it from overgrowing with biology during intermittent or even continuous use. So that's what it was originally designed for, was as a pre-treatment step for RO and NF when people were struggling with either biofilm sloughing off into their membranes, or they didn't have room, or they couldn't afford the water for redundant tanks and redundant processes.
We kind of laughed and we said, well, if you want skunk-free carbon, this is probably the way to go. Or skunk-free carbon filtration dechlorinator.
Yeah, I mean, your carbon dechlorinates in the top layer of the bed, and then everything below that. And it's not, I mean, it's only detrimental if the biofilm starts to shut off active sites on the carbon. So that forces you to backwash it probably more often than you want. There are ways to try and clean carbon. And again, it's all painful to do. Adding disinfectants during backwash, steam cleaning, or whatever people are trying to do. So this product was designed to help improve overall filter performance. It actually reduces, it's got a lower backwash rate than most GACs, and it's got a way lower backwash rate than most multimedias. So there's economic savings in water with that bacteriostatic performance that you get from the alloy. We've tested it. We've sent it to labs. We've tested it in elevated temperatures, throwing bacteriophage at it to see what it'll do. We know it'll be bactericidal, but we don't make any claims on that. It definitely is bacteriostatic. It will not grow any bugs in an idle environment. So we figured out how much alloy to have to make that functionality happen. So
yeah, I mean, if you have let's say a pond or a big, say, pool of bacteria coming into this thing, you should kind of correct that. But what we're saying is it will basically keep the bed from becoming a bio-growing environment.
Yeah, there were other products that people were adding to the top of softeners and filters to try and put a bacteriostatic layer in there. And my understanding those products have gone away.
Yeah.
Now you add a solid alloy, it ends up at the bottom of your filter. It becomes a support bed. It's still, alloy is a good product. It still does what it needs to do, but it's after the fact. So now you've already got biofouling in your material. Now the alloy's there to help undo something that you could have prevented.
Exactly. Good point. This product, it stays stratified because it's attached to the substrate, which is the ceramic. So we were alluding to the cubes, which went extinct. We found that sometimes those cubes in a backwashing filter will then migrate down through the carbon or the media, and then the top of your bed can become contaminated, where it stays within the whole column. It treats the whole column.
The cubes would have accumulated mass. So they collect dirt, they get heavier, right?
Exactly.
And the other thing that happens is if you have a filter with a broad particle size, your bigger particles always end up at the bottom and your smaller particles end up at the top after a backwash. That's just the way Mother Nature organizes things based on size and mass and the way things are in a fluidized bed. Because we've scalped out the oversize and we have a really homogeneous sort of, all the media is more or less the same size, it also moves around. So the stuff that's at the bottom doesn't always stay at the bottom, and the stuff that's at the top doesn't always stay at the top. So that helps us keep the bed fresh and move the material around after backwash. It does make a tighter, better filter. So sometimes you just got to pay attention to backwash frequency and pressure differential. You use your word skunky water that's got a lot of particulate in it.
Yeah.
You might have to backwash a little more often, but our backwash rates are lower and your effluent water is going to be cleaner. So those are the trade-offs.
Yeah. Also, it's a darn good filter. On top of the alloy and the carbon, it's a really good filter down to 10 microns all day long. And sometimes, like almost like 5, where we see other products out there that claim that with a zeolite, a natural clinophthalite kind of zeolite material, but you take it one step further with the alloy. So I'm thinking there's so many whole house ROs being put in out there. This would be a darn good product to put in before a whole house RO, especially if it's well water and you got a little bit of sediment also. It would be really good to put that in there. Nothing iron bearing or manganese bearing. We have products for that. But if you want to dechlorinate city water, that's just, people want to have a whole house RO on that. But if you have well water and you don't want to create a biological situation, which I would imagine some of these whole house ROs are on TDS at 1200, they become a host for a lot of other things with the high TDS. But would high TDS hurt this? Because that's a question. Alloy sometimes got a little, what do you think the limits there? Because a lot of guys are putting whole house ROs on, and because of high TDS, say 1200 in there. What do you think?
There's a couple points there. High TDS, right? From a biological perspective, if you have carbon, which is DOC or TOC, right? Total organic carbon or dissolved organic carbon, which in higher TDS waters can happen. If you have carbon source and you have phosphorus, so you have a little bit of phosphate in the TDS or any ammonia, you have a perfect place to grow biology. Mm-hmm. So the higher the TDS, the more likely that stuff's going to happen. So there is the risk of higher biological activity if you have a carbon source and it gets a little warm, and right, it's a nutrient-based thing. But moreover, TDS hurts a lot of filters, right? And I'm not going to take you down a filter rabbit hole here where we get into boundary layers and stern layers and London forces. But basically, as TDS goes up, it's actually harder for filter medias to filter out colloidal and small particulate, things that would turn into silt density index, SDI, right? Which is your particle metric for treating membranes. People forget that SDI is how you measure the potential flux rate for your membranes. And the particles that make up SDI can be down as small as 0.45 microns. And those particles get harder to filter as TDS go up. And it has to do with the complexities of the water and the charge. It compresses charges around particles, blah, blah, blah. So having a tighter filter and a better filter on a whole house RO and high TDS kind of goes hand in hand. That's where having a better filter will improve your performance of your filter just by virtue of having something that works a little better and that is a little tighter. So those are the two things that come to mind.
Okay. Well, I think we've covered it quite well. I mean, as far as, we try to keep these a little short. That's where I'm going.
Well, you pretty much tapped me out at this point.
Yeah, I think so. I think we got, and you can hear me fumbling around. I'm like, well, yeah. I think we've built the excitement. And, of course, this is maybe a shameless infomercial, which we usually don't do. But I just think it's a good product that fits now because KDF is really heavy and the cubes are extinct, and I had a void in the product line. And not that I've not known this product for a while, but the other stuff I was dumb, fat, and happy. And now this stuff here, the CeraPure AC, is, I think, quite the product. So hopefully some people, you could go to our website or give me a call about it. But thanks for doing this, Derek. Really appreciate it. Despite I had a little technological glitch here, so that's why Derek might be sounding like he's on his cell phone, and he is. So thank you, Derek, and trust the frog, everybody. Thanks for listening. Bye-bye.
This podcast was edited by Resonate Recordings.